Okay, so we are in Statistical Rethinking, second edition. We're in chapter 9, and we're on the hard questions. We're on question 9H2. Okay, so we are to go back to a model that we played with in earlier chapters, chapter 5, the divorce model. I believe it's called waffle divorce. Yeah, the data is called waffle divorce. And I'll show you the models here, or you can look in the book. And so we're going to repeat that analysis, but if you recall, we've only now learned how to use Monte Carlo, Markov chain Monte Carlo with the ulam command. And previously we were using a different method that's called QAP in the rethinking package. So we're going to refit those models, but now using ulam. So we're going to refit models M5, 1, 2, and 3. And then we're going to compare the models with WAIC and PSIS. What's important here is that when we are using ulam or Markov chain Monte Carlo or STAN in general, if we want to use these methods, we need to insert an argument called, it shouldn't be called log, it should be called log-like. Let me change that here. It should be called log-like for log likelihood, because we need the we need the log likelihood. We need a value that is calculated for the log likelihood, because those are the things that actually get used by WAIC or PSIS. Okay, so I'm just getting the data in order. All right, so remember we standardized everything, and so I've just copied and pasted this from the book. Okay, and then I'm packaging it into a list here. Because ulam and STAN tend to prefer using lists. So I have my standardized divorce rate, my standardized marriage rate, and my standardized median age of marriage. Okay. So now I'm going to run the models, or I've already ran them, so you don't have to sit here and watch it run. But so I have M5-1, and for M5-1, we are regressing divorce rate only on age of marriage. And M5-2, we are regressing only on the marriage rate, right? Divorce rate is being regressed on the marriage rate. Didn't want to do that. Okay. And then here we have divorce rate regressed on both age and marriage rate. Okay. So I've ran all of these. Go down. Okay, and so now I'm going to compare all of these things, and just to make it more readable, I'm going to round these. Rerun that. Okay, that's a little bit better. Okay, so let's look at the output here. Okay, so remember that with these compare functions, what we get is a readout where the models are put in rows according to how good they're doing with whatever metric we're using, right? So here we're using WAIC, and M5.1 scored the lowest on WAIC, and lowest is better, quote unquote better. And so M5.1 does better than 3, does better than 2. Okay, and so then we get the WAIC score here, as well as the standard error of that score. And then for DWAIC, we get the difference between whatever model and the top model, right? So the difference between M5.3 and M5.1 is 2.3. Okay, and then we get the standard error of the difference. Okay, and then we get the penalized. I can't remember what this is called. The penalized likelihood, or the size of the effective numbers of parameters. Okay, and then over here we have weight. Okay, and so that's saying that it's an ensemble. How do I want to explain this? It's saying, okay, if I had these three models to make predictions from, I would want to weight the prediction of M5.1 76 and M5.3 24, and give 0 weight, or approximately 0 weight, to M5.2. Okay, so that's what's happening in these tables. Okay, and similarly, that was for WAIC, and then the same thing for PSIS. Okay, and so we see that in both models, M5.1 is ranked top. Okay, and all the values are pretty similar between the two methods, so that's interesting. Now, notice that the age-only model does the best in both instances, okay? Which is interesting because it actually uses less parameters than M5.3, which not only has age as a regressor, but also has marriage rate, okay? And so what this is saying, the fact that M5.1 is outperforming M5.3 is that there was a cost of adding that additional variable, right? And there was a cost in the uncertainty, and that cost was, how do I want to say that? There was a cost and uncertainty for adding the parameter of marriage rate that made the predictive reliability of M5.3 to be worse than M5.1. So I hope that makes sense. So that's kind of what's happening here. But notice that that M5.3 isn't performing much worse than M5.1, and in fact claims about a quarter of the ensemble weight. So it's not that M5.1 is a unanimous favorite. It's just that M5.3 is it's not unanimous, but they both probably have some predictive value. So why would adding a predictor variable to M5.3 make it perform worse than M5.1? Okay, so I've kind of discussed this a little bit, but let's look just at the PSIS output for M5.3 here. Okay, and this is so BM is the parameter that we added, the beta for the median marriage rate. I'm sorry, median marriage rate. Okay, and notice that this parameter hovers around 0 and is very uncertain, right? So it kind of straddles 0 on both sides, right? So adding marriage rate, there's a lot of uncertainty inherent to that, and so it's not adding a lot of predictive value, and adding that parameter there's a penalty incurred by adding that parameter in WAIC and PSIS that is not being paid for in predictive reliability. Okay, so that's kind of what's happening here. Now, that is not to say that in an absolute sense, marriage rate is not important in divorce rate. Okay, in some way, almost tautologically, it has to be. But it's just saying that in terms of predictive accuracy, when we're that including marriage rate, given our data, there is a larger risk of overfitting for having included that parameter. Okay, so now there's also another issue here. If we go up here, we notice that, so here we don't know what this is referring to, but we see that two of the models, when we ran PSIS on them, had K values that were greater than 0.5, okay? So if we run this code, PSIS, and then we have the three models, and we use pointwise true, we get the K values for every observation for each model, and I mean, there's a lot there, more than I really want to look at, but at the top of each of these, so we get the warning for the model that has these, maybe semi-high K values, okay? So it looks like model 1, not model 2, and model 3 have these high K values, okay? So just to say something about that, I guess. So usually K values are thought to be reliable as long as they're below 0.7. But the fact that we have two models that are a little bit, that are maybe threatening to be a little bit high, may call into question the reliability of these PSIS and WAIC scores altogether. So in which case, we have to be a little bit careful about accepting the readouts from WAIC and PSIS, okay? This can be a little bit frustrating because I don't really know what else to resort to compare these models other than something like physically, or to actually encode or to actually code some kind of cross-validation method, which can be very computationally expensive when we get into these ulam models. But anyway, I guess I will call that good here.